Hi everyone and welcome to this video on geometry of simultaneous linear equations. Today I'm going to talk about the three situations that you can see on screen at the moment, and I'll start this off by saying that over the last probably 8 years or so this style of question has been very common on the end of the year exams for math methods, and that it has appeared on both exam 1 and exam 2, so you're expected to be able to do this by hand and also using your calculator. We're going to go through both strategies today. So to begin with, we're going to look at the different types of solutions that we can have when we're talking about simultaneous linear equations, okay? Remember that when we talk about solving equations simultaneously, what we are finding is the coordinates of the point of intersection. And so these are the three types of solutions that we can have. We can have a unique solution, so like this, where the two lines cross and they have a point of intersection right here. Okay, so they are going to have one solution. These lines are never going to cross again because they continue in a straight line, so they're not going to bend back around to intersect again or anything like that. We can have no solutions in this situation here. So no solutions occur when we have parallel lines that have different y-intercepts. And we can also have infinite solutions, so that's happening right here. And that's when we have two equations that have the same line. So sometimes the equations will be identical, other times they will be a bit different, but they'll just have like a common factor or something like that that could be taken out to make them the same. So to begin with, what I want to do is I want to consider just the general form of an equation in its intercept form. Okay. Now, I said that when they have no solutions, they have to have the same gradient. They are parallel lines. And we can see that for infinite solutions, they have to be parallel and they have to have the same y-intercept. So I want to consider this general situation so we can see which parts of the equation are going to influence the gradient and the y-intercept. So if I rearrange this equation into its gradient and y-intercept form, then we should be able to see it. So I'm going to start off by just subtracting ax from both sides. So by equals negative ax plus c. And then I can divide everything by b to get y equals negative a on b x and then plus c on b. So this is always going to be the case for linear equations when we rearrange them into their y-intercept form. What we can see here is that the gradient, negative a on b, so those a and b values are these values right here. Okay, the gradient is determined by the coefficients of the x and y term. So if we have two equations and they have the same ratio between these values, then they're going to be parallel lines. And likewise, the y-intercept just here is given by the ratio between the c value, so the number on the right-hand side of the equation, and the coefficient of y. Okay, and that will always be the case. So if I come back up here for a second, for a unique solution to exist, we need to have no common ratio between coefficients of x and y. So, for example, the equations could potentially be something like 2x minus 3y equals 5 and 4x plus 7y equals negative 2. Okay, so there's no common ratio there. 2 in ratio with 3 would not be the same as 4 in a ratio with 7. So that's what we're sort of going for there. Now, to have no solutions, they needed to have a common ratio between the between the coefficients of x and y. So that's going to give them the same gradient, but we want the y-intercepts to be different, so we don't want the ratio between the c and b values to be the same. So in this case, I could have two equations like, perhaps I'll write that first. So here it was a common ratio between a and b, but not b and c. So for example, we could have equations like 2x plus 3y equals 7, and then 4x plus 6y equals 5. So here we would have the common ratio between the a and b values. So 2 to 3 is the same as 4 to 6 because the 4 to 6 can be simplified. But the ratio of the 3 to 7 would not be the same as the ratio of the 6 to 5. And the last one, we need to have common ratio of a to b and also b to c. So here, to have equations that have infinite solutions, they essentially need to be the same equation. So we could actually have two equations that are identical, or we could have, for example, x plus 4y equals 12 and 4x plus 16y equals 48. So we can see that the second equation is exactly 4 times the first equation. So moving on, state whether the following pairs of simultaneous equations have a unique solution, no solution, or infinite solutions. So if we have a look at the first one, well, we can consider the ratios 2 to 5. So does 2 to 5 equal 6 to 15? Well, hopefully we could just divide each of these numbers here by 3 to get 2 to 5. So yes, that is holding true. Okay, so we have the common ratio there. Now for the ratio of b to c. So is the ratio of 5 to 8 the same as the ratio of 15 to 12? Well, I don't think so, because 5 to 8, like the number's getting larger there, but 15 to 12 it would be getting smaller. So these are not equal to each other, and so we don't have that common ratio between b and c. And so this is a situation where we have the common ratio between a and b, but not b and c, which means we are dealing with no solutions. Okay, so the second equation, or the second set of equations, 5/7 x minus 3/4 y equals 12 and 40x minus 42y equals 672. So we're going to test 5/7 in ratio with 3/4, and we want to see if that is equal to 40, and I should have made a point of saying negative 3/4 there because it's 40 to negative 42. So this one here isn't as easy to do, and you could do this using your calculator. Remember that this ratio sign here just means divide. So if you just type in 5/7 divided by negative 3/4 and then type in 40 divided by negative 42, you would see what they are equal to, and if they are equal to the same thing, then that's good. So I might actually just go ahead and do that. Got a little bit of other stuff set up here for in just a moment. So might even just highlight that, drag it down here, and make that divided by. So 5/7 divided by 3/4, and it should be negative 3/4 is that. And then 40 divided by negative 42 is that. Okay, so they are in fact the same value, and so those numbers are in a ratio. So the next thing is to test the other ratio, which is negative 3/4 to 12. Is that the same as negative 42 to 672? Well, again, I'm going to just use the calculator here. So negative 0.75 divided by 12. And then negative 42 divided by 672. Helps if I don't have the answer there. Okay, so they are again in the same ratio. So this ratio is true as well. And so now we have both ratios occurring, which means we are dealing with infinite solutions. And the last one, well, we can see x, so 1 in front of the x to 3, and in the second equation we can see 1 to negative 3. So we can see straight away that those numbers are not going to have the same ratio. One would be the negative of the other. And so this is a case of unique solution. It looks a little bit similar, but because of the minus sign, it does make a difference there. Anyway, I'm going to leave this video here, and we'll pick up the next example in the following video. This next one I'm going to do is very much an exam style question, so we'll get stuck into it then. See you.